Hey everyone, welcome back to Cracking the GRE Math Subject Test. This is Calculus 2, and we are on question number 11. So, in this question, we are given three piecewise defined functions, f1, f2, and f3, and we're asked which of these functions is or are continuous at the origin. Remember, continuous means that the limit is equal to the value of the function at the origin. So, the thing with functions that are defined on more than one variable is that no matter how you approach the origin, when you take the limit, you have to get the same value. And so if we take a look at f1, let's try to investigate f1. If we take the limit as x, y goes to 0 along, let's say we want to approach 0 along the x-axis. That means that along the line y equals 0. Y equals 0 is the x-axis. Then what are we going to get? Well, then the limit of f1 is going to be, well, take a look at this expression. If we put y equals 0, then we get x over x, which, that limit, this would be the limit of, as xy goes to 0, of x over x, which is 1. So that might work, but it's not enough. That's not sufficient to say that the limit actually is 1. Let's try to approach the origin along the y-axis. So let's take the limit as xy goes to 0 along x equals 0. So in this case, we're going to have the limit as xy goes to 0, but now we're going to place x equals 0. So we'll have negative y over y. And then we get a limit of negative 1. So you see we get a different limit depending on how we approach the origins. That means that the limit doesn't exist, and it's definitely not equal to 1, which is what the value of the function is at 0. So f1 is not continuous. So that's an x. Let's take a look at f2. For f2, let's try the same strategy. If we take the limit as xy goes to 0 along y equals 0, then we're going to get, let's plug in 0, we'll get 0 over x squared. Alright, so this will be limit of 0 over x squared, which does equal 0. Actually, if we do the same thing with along x equals 0, we'll also get 0, so that looks promising. But if we take the limit along the line y equals x, then what do we get? Well, we'll get the limit. If we plug in y equals x, then we'll get x squared over x squared plus x squared is 2x squared. And here we can cancel out the x squareds and we'll get 1/2. So you see, as along the line y equals x, the limit is 1/2. And that means that this is not continuous, because depending on how you approach the origin, you're going to get a different limit. Alright, well, let's take a look at f3. For f3, let's try the same things we tried before. If we plug in y equals 0, then we'll get x cubed over x squared, which cancels and you get x. So as you approach 0, this is going to go to 0. So that looks good. But what about x equals 0 along the y-axis? Then we'll have negative y cubed over y squared, which, yeah, that also is going to approach 0. What about along the line y equals x? Well, in that case, we'll have x cubed minus x cubed. So that'll be 0 over 2x squared. So yeah, that's going to be 0 all the time. So far, all these test cases seem to indicate that f3 is continuous, and it always approaches 0 as we head towards the origin. If we wanted to actually prove that this is the case, then we could switch over to like cylindrical coordinates and write, remember in cylindrical coordinates, x is r cosine theta. So we could write f3 of r theta is equal to r cosine theta cubed minus r sine theta cubed all over x squared plus y squared, that's just r squared. Now we can factor out an r squared, and that'll give us r squared times r cosine, r squared times, and we can factor out an r cubed actually. Yeah, we can factor out an r cubed. So then we get, let me rewrite that. We'll get cosine cubed theta minus sine cubed theta. Sine cubed theta. And then the r squared in the denominator is going to cancel out with 2 of the r's in the numerator, and we'll have r times cosine cubed minus sine cubed. Now what you can notice here is that cosine cubed is always between -1 and 1, and same thing with sine cubed. That's also always between -1 and 1. So the whole thing inside the brackets is always going to be between -2 and 2. And so this thing is always going to be, let's say, between -2r and 2r. So this is always, so we can say that f3 of r theta is always going to be between 2r and -2r. Now we know that as we can approach, if we approach the origin by taking the limit as r goes to 0, then by the squeeze theorem or the sandwich theorem, then we know that -2r goes to 0 and 2r goes to 0. So therefore f3 also has to go to 0. So that proves that f3 is continuous at the origin. So our answer is f3 only, D.